We are now going to move on to talk about the early Earth and the formation of the moon. You just watched a video called The Early Earth, and I want to make sure we're clear on the key concepts. First of all, how and when did Earth's core, mantle, and crust form, and what did density have to do with this process? Earth began as a homogeneous planet. Homogeneous means everything is the same. And in this case, what was the same was the composition. Composition is what something is made of. For example, salt, you may be familiar with, is sodium chloride. That's what salt's composition is. It is the same throughout. And so Earth's composition, which was a little more complex than just sodium chloride, was the same throughout. Earth was very hot early on. The two main sources of heat included the heat of formation, which was from collisions and bombardments that made Earth get larger. If you recall in the video, they were talking about how when you clap your hands, you feel heat. And so look at how large the Earth is and imagine how much heat was absorbed by all those collisions. In addition, Earth has become hot from the decay of radioactive elements. As a result of Earth getting so hot, Earth actually melted, and we believe that early Earth was maybe melted all the way through. As a result, Earth behaved as a liquid, and elements that were dense, such as iron, were able to sink to the center of the Earth. Elements that were lighter, such as silicate minerals, rose to Earth's surface. Now, I know you might not know what silicate material is yet, but it's basically the material that makes up rocks on Earth's surface, and we'll be spending a lot of time looking at those. If you look at this cartoon here, you'll see this is supposed to be the Earth, and all of the little red items are the iron sinking down towards the center and forming Earth's core. The less dense material is the silicate material, and that's essentially floating towards the Earth's surface. This process is called chemical differentiation, kind of a fancy word for the Earth separating into layers. Let's remember density. Density is mass divided by volume, and we're going to use density a lot in this class. The density of water is 1 gram per cubic centimeter or kilogram per liter. And I'm going to use kilograms per liter in this next example because that's what's shown in the diagrams I'm about to use. If something is more dense than water, it will sink. If something is less dense than water, it will float. So let's take a look at this first example. I have a block of wood right here floating in some water. If you look at the top, I've got some information about the wood. I have its mass and its volume in kilograms and liters. And if I divide the mass by the volume, I get the density, which in this case is 0.4 kilograms per liter. And remember, water is 1 kilogram per liter, so the wood is less dense, so it floats. This would be similar to the silicate minerals floating to the top of the Earth's surface. Here I have a brick. The mass and the volume of the brick are shown. When put into the density formula, give us a density of 2 kilograms per liter, which is more than 1, and so in water, the brick sinks. This would be similar to the iron in Earth's interior. So density causes it to sink. And so back to the same picture, that's what's happening in this diagram right here. Now, of course, the orange stuff isn't water, but it's some material that has a density somewhere between the silicate and the iron minerals. And so we have the Earth now today in layers. We have a crust, a mantle, and a core. The core is mostly iron, the crust is mostly silicate minerals, and the mantle is a combination of the two. Sometimes people like to think about the layers of the Earth as a hard-boiled egg, with a yolk, the egg white, and the shell representing the 3 different layers. Let's move on to the next concept. How did Earth's magnetic field form, and why is it important for the formation of Earth's atmosphere? So first of all, the magnetic field has been produced by a flow of electrons in the liquid outer core of Earth. And we'll talk more about this when we talk about plate tectonics, and we talk a little more about why Earth's magnetic field is very important to support the theory of plate tectonics. But this magnetic field couldn't form until we had a core, of course. So once we had a core, we had this flow of electrons, and this produced our magnetic field. And the magnetic field protects us from what's called the solar wind. The solar wind is a stream of charged particles that comes out from the sun in all directions. It isn't really a wind, it's just called a wind. It's just a stream of charged particles. And if those particles hit the Earth unprotected, then any atmosphere building up in the Earth is just blown away. Again, not really a wind, but stripped away with these electrons. Once the magnetic field was there, the solar wind is deflected around our magnetic field, which the magnetic field here is indicated by these kind of bluish, lobe-like structures. How did Earth's atmosphere form? Well, primarily from outgassing from volcanoes, and that's similar to what happens today. The primary gases that come out are carbon dioxide and water vapor. Now, that's not a very good breathable atmosphere, so we'll get to the oxygen part of our atmosphere later. But the earlier atmosphere was pretty much this. Some other things like methane and ammonia. Also, many scientists believe that comets brought some water as well. Here's an artist's depiction of what the early atmosphere might have looked like. Again, not very hospitable. How did Earth's oceans form? And what evidence do we have for the oldest age of the ocean? Well, the early oceans formed basically from the water in the atmosphere condensing, becoming rain, and accumulating in the ocean basins. So here's our outgassing forming our atmosphere. Our water vapor eventually condenses to a liquid and it forms clouds, and those clouds rain and fill up the ocean basins. The evidence we have for the oldest ocean are rocks that are formed by oceans. And so here are some rocks, they're called sandstone, and inside of them is a little grain called a zircon, and that zircon grain has been dated radiometrically at 4.4 billion years old. And because this rock is formed in the ocean, this suggests that the oceans were around as long ago as 4.4 billion years. So pretty much very early in Earth's history. One thing that the video didn't talk about, which is important in Earth's early history, is how the moon formed. The common theory is that there was a giant impact between a Mars-sized body and Earth very early in the solar system's history, pretty much 4.6 billion years ago. And so here's an artist's depiction of what that impact might have looked like. Here's another series of them. So here's an object colliding into Earth. This would be the Mars-sized object, not the moon, but an object colliding with Earth. It hits Earth, kind of merges with Earth, and throws off a bunch of Earth's mantle material. That material ends up spinning around Earth, almost like the rings of Saturn, and slowly cools, and the material collides and forms together, and it becomes the moon. So here we have the Earth-Moon system. The evidence for this was brought back by the astronauts when they brought moon rocks back. It turns out the rocks of the moon and the rocks of Earth are chemically very identical. They have very similar what's called isotopic signatures in a way that they have to have some sort of common origin. Other moons, such as the moons of Mars, are believed to have been captured asteroids that were zipping around the solar system when the solar system was forming, and Mars caught them in its gravitational pull, and they just continued to orbit Mars, but they never interacted with the planet. Because the rocks from the moon are so similar to Earth's rocks, we believe they had some sort of common origin, such as this idea here. Now, I hope you are all looking at your textbook, free textbook online, and noticing that sometimes there are little videos. So this is in Chapter 8. This is Section 8.3.2, Origin of the Moon. And there's a little 2.5-minute video called Evolution of the Moon from NASA. And if you play it, it'll show you this really cool computer-generated image of the formation of the moon. And so here it is 4.5 billion years ago where it's just cooling off. I've just taken a few snapshots here. Here's a period of bombardment when large objects are bombarding the moon and causing magma to come to the surface, and that's what winds up forming the dark parts of the moon. And then here's a period of time where there's an intermediate bombardment history. And anyway, it's a really cool visual of the formation of the moon. I encourage you to check it out. Coming up next, the Great Oxygenation Event.